So now I'm going to show you the recycling process and the design. And for this, I'm going to show you a video where it is explained how the material recovery facility works. So the waste is collected as mixed refuse, and then the materials are removed by various processing steps. We are going to discuss later each equipment and what is the main the use of this equipment. In separating any one material from a mixture, the separation is termed binary because only two outputs are sought. Look, this doesn't mean that you only have two types of materials. It means that you have one target material and then the other ones are the ones that are the rejected ones. So that's why we discuss in terms of binary separation, all right? And this is going to be important when we discuss the design and the base or mass balances. When a device is to separate more than one material from a mixture, the process is called polyinary separation. This is on the right side, you can see a diagram of a typical material separation facility for refuse and refuse processing. So these are the type of equipment that we're just going to briefly explain. So the objective is separation of the X fraction. So as I mentioned to you before, if the equipment is meant to separate aluminum, X will be the target, right? The first exit stream is to contain the X component, but the separation is not perfect and contains an amount of contamination. So the contamination can be other material that are in the mixture, a part of aluminum, in this case, as the example that I have made. This stream is called the product or extract, while the second stream, containing mostly Y, but also some X, is the reject. The percent of X recovered in the first output stream, R, may be expressed as, so this is R and it means recovery and is based on how much was recovered from one target material, that is the target material is X, all right? And X0 is the initial amount of material, while X1 is the amount of material that was recovered. Okay, and is multiplied by 100. We are not going to only base the calculations on terms of recovery of the materials. We are going to also base in terms of purity. So that means that not all the target material that we are extracting are 100% pure. It can have some impurities. And how are we going to define these impurities? By the following formula, which is pretty simple, right? It's how much do we have on X1 and how much do we have of X1 and Y1. So as you can see on the right figure, is a diagram of a binary separation that I'm explaining to you, where I say target product, but we can also call it desired product, X, and Y is the rejected product. So all these two enter into the binary separation. Reject product can contain more than one product, material, as I explained to you before. And the material that is rejected can be later on be recovered in another stage, which that will mean that the second target material will be now X, or will be now the target the new target material, all right? So X0 and Y0 enter into the separator, and then we have an output where we have on the outlet number 1 mostly the material that we are aim to recover, and on the line or the output 2 is the rejected material, but it can also contain some desired product depending on the efficiency, right? So now we're going now again to the left side to explain what is the separator efficiency. So the performance of a material separator is assessed by purity and the separator efficiency. So the general expressions for material recovery are, as you can see, simple equations that are based on mass balances, and those are the ones that we're going to use to make some calculations and getting efficiencies, and also discussing these efficiencies against reduction of greenhouse gases or energy. Now I'm going to have a brief discussion about the type of equipment that is being used. These are the screens, and these are used to separate material by size and not by the property of the material, right? This is the most basic type of separation. These are often used for classification. Then we have air classifiers, and these the materials can be separated by the aerodynamic properties. And in this type of equipment, the principle is the separation based on the density. So we know that less dense materials are organic and most of the denser materials are inorganic. Magnets are used to remove ferrous material. With the belt magnet, recovery of ferrous material is enhanced by placing the belt close to the refuse. These are one of the most important components, just because the high value of metals enhances or stimulates the recovery of this. So there are some other equipment that is actually mainly used in the recovery process nowadays, and these are froth flotation and eddy current devices. So flotation has been successfully employed to separate ceramics from glass. Flotation is a process that selectively separates materials based upon whether they are water repelling, hydrophobic, or have an affinity for water, hydrophobic. Eddy current devices are used to recover non-ferrous materials such as aluminum. Eddy currents are loops of electric current which is circulated in a conductor by changing the magnetic field in it. When the current flows through the conductor, an eddy current will produce its own magnetic field. Now that we have discussed the principles of recycling, we are going to start doing an example of a binary separator. A binary separator, a magnet, is to separate a product, that is ferrous materials, from a feed stream from shred refuse. The feed rate to the magnet is 1000 kilograms per hour and contains 50 kilograms of ferrous materials. The product stream weighs 40 kilograms, of which 35 kilograms are ferrous materials. What is the percent recovery of ferrous materials, their purity, and the overall efficiency? Okay, we're going to start now with the example. Let's organize first the information that we have. So we have the value of x1, that is 50 kilograms per hour. Everything is per hour, by the way. We have the input, the total input flow, which is 1000 kilograms per hour. So now we can actually know already the value of y0, which should be 950 kilograms per hour. Then another additional information that we have is the value of the output in 1, and that's equal to 40 kilograms per hour, and x1 is equal to 35 kilograms per hour. So then we can already know then the value of y1, which should be 5 kilograms per hour. So now we are going to define we have two options here at this moment. We can solve the overall mass balance by making mass balance on x and y. And x0 equals x1 plus x2, y0 equals y1 plus y2, or we can start using the formulas of the efficiency, separator efficiency, recovery efficiency, and purity. And from that we can start seeing what information we have or we missed, right? So we can now start the recovery efficiency. And the recovery efficiency equals to x1 divided by x0 times 100, and this should be equal to 70%. Then for the purity, this is equals to x1 divided by x1 plus y1, and we have all the values already, as you see above. So then we can calculate this number, right? Which is 87.5%. And for the separator efficiency, x1, x0 multiplied by y2, y0, we need information. So we have these two values, and we are then able to calculate y2, which is equal to 945 kilograms per hour, and with this value now you can calculate the efficiency, and the efficiency should be 87%. Now, important things to keep in mind. When you have an exercise like this, you may not have all the information on the inputs and outputs, but you might have the efficiency of the equipment, for instance. And based on the efficiency of the equipment, well, you can calculate the other streams, right? You can have also information on recovery or the purity. You can remember that we're dealing with a binary separator, but that doesn't mean this is the target, the desirable one. And this one, Y0, can have many other materials. So it can have, the target can be, for instance, let's say aluminum, and the second one can contain ferrous materials, paper, glass, etc., right? If we move this separator, which in this case is a magnet, but can be an eddy current or another type of equipment, and this stream now goes to another equipment, we start again the mass balances, and now we need to find which one is the target or the desirable, and which materials are the rejected ones, okay? They will change. So please keep in mind this for the tutorial on material. Now, let's think beyond the simple mass balance that we're doing now. So what can we do with the information that we obtain? So from this information, we can actually make a case for encouraging recycling. How can we make a case? We can actually calculate how much CO2 emissions are being reduced if we recycle a percentage of the material, or we can also we can actually also calculate energy, right, in terms of energy. So this is the importance of getting this information. previous slides, on previous slides, you already have the kilograms of CO2 per kilogram of material. The total when it's coming from virgin materials. So from that, you can actually get this information, and that's something that you will have to do on the tutorial.